Have you ever looked at a news headline, filled with numbers, cases are up by X%, or mortality rate is Y in this region, and felt like maybe you were missing a crucial piece of the puzzle? You know the numbers are important, but what are they really telling you? It's easy to feel overwhelmed, right? To just skim past the data. That's exactly why we created the deep dive. We want to cut through that noise and give you the foundational insights you need to truly understand what's going on. Today, we're taking a deep dive into the foundational elements of how we measure health and disease in entire populations specifically, the basic measurements in epidemiology. Our mission here is to help you understand the precise tools and logic epidemiologists use so, you can decode those headlines yourself.
And that mission is really critical because understanding why precise measurement is so important isn't just some academic thing. It's the absolute first step. It's fundamental to understanding and, well, ultimately improving public health. What looks like a simple number often has layers of complexity behind it that completely determine its true value and, its meaning.
Okay, let's unpack this then, because there's a surprising distinction right off the bat that I think can really reshape how you think about medical data. A clinician, like, say, a doctor treating you one-on-one, might not need an incredibly precise, universally agreed upon definition for something like a migraine for immediate patient care. They're focused on your symptoms, your treatment. But an epidemiologist absolutely does need that precision. Why? Why such a big difference? What's really at stake there?
Yeah, it really comes down to scope and scale. You see, a clinician is focused on the individual patient right in front of them. But epidemiologists, they're looking at entire populations, hundreds, thousands, millions of people. So when you're studying a large group, you need definitions that are, first, acceptable and applicable to those populations. And crucially, they also need to be precise and valid. That's the only way to clearly identify who has a disease and who doesn't consistently. This precision, it's vital because it helps minimize errors in how data gets classified. Think about it. If different researchers define the same condition differently, you're not just comparing apples to oranges. Sometimes, you might be comparing apples to something completely different in your conclusions. They'll be completely off. That's why standardized methods of observation and recording have to be in place before any study even begins.
Ah, okay. That makes so much sense. Consistency is key for comparison. And here's where it gets really interesting for me. The sheer breadth of what epidemiologists measure. You mentioned it's vast, almost unlimited. What kind of things are we actually talking about here?
Well, it truly is immense. I mean, we're talking about everything from the most fundamental measurements, mortality, which is death, and morbidity, which refers to disease or illness, but also things like disability and natality, that's births. And beyond that, epidemiologists also track the presence, absence, or distribution of specific disease characteristics or attributes. Think about, like, the presence of a rash in measles. That's a data point. But it doesn't stop at the individual level. They also measure medical needs within communities, the availability and, importantly, the utilization of healthcare facilities and services, plus a wide array of other health-related events. They even track environmental factors, the presence or absence or distribution of things suspected of causing disease. And, of course, critical demographic variables, things like age and sex, which influence pretty much everything in health.
Wow. And even with that incredibly expansive list, our source material points out some intriguing areas that aren't maybe fully covered yet. Things like the psychosocial aspects of health and disease, or the need to better identify components of, overall well-being. It sounds like a field that's constantly evolving.
Absolutely, it is. And while all these measurements ideally must meet basic requirements like validity measuring what they intend to measure and reliability getting consistent results, it's really important to remember something. Errors are unavoidable. In any measurement, it doesn't matter who's taking it or how precise they try to be, some error creeps in. So the purpose of quality control isn't really to eliminate errors entirely. That's basically impossible. It's to reduce them as much as possible, or at least down to an acceptable level that doesn't, compromise the study's integrity.
Okay, that's a realistic perspective. So to really get a grip on these measurements, we need to decode some foundational terminology. The terms epidemiologists use to categorize their data. Let's start with variate. What exactly is that?
Right. A variate is basically any single piece of information that refers to a patient or their disease. Just think of it as a single data point. Now, variates can be discrete. That means they're either present or absent, like a diagnosis of lung cancer, yes or no, or a broken leg, yes or no, or the presence of that rash we mentioned, yes or no. Or they can be continuously distributed. This means they fall somewhere along a scale. Things like blood pressure readings, serum cholesterol levels, or a person's height.
Got it. Discrete is yes, no, continuous is on a scale. Okay. And then there's circumstance. How does that fit into the picture?
So a circumstance refers to any factor in the environment that might be suspected of causing a disease. For example, we might consider a specific level of air pollution as a circumstance, or the presence of a particular contaminant in the water supply. Now, when we're looking at these discrete variables or circumstances, the yes-no kind, their frequency is typically expressed as a rate. It's about relating that frequency to a population size. But for continuously distributed variables or circumstances, the ones on a scale, their frequency is usually expressed using a frequency distribution. And that's often summarized by things like the mean or percentiles or standard deviations.
Okay, so we have these building blocks of data variates and circumstances. Now, what are the core tools epidemiologists use to actually express the magnitude of disease in a population? You mentioned rates, ratios, and proportions earlier. I get the sense that truly understanding the difference between these three is critical if you want to interpret any epidemiological data you see, like in the news or in reports. Let's start with rates. For instance, if I simply tell you, hey, there were 500 deaths from motor vehicle accidents in City A during 2010, that feels like a big number, right? But for an epidemiologist, that number alone isn't enough, is it? Why is just counting not sufficient to draw meaningful conclusions, especially if I want to compare, say, City A to City B?
Exactly. Just counting the number of events, what we call the numerator, doesn't tell us about the risk or the burden of that event in the population. 500 deaths sounds like a lot, but is City A huge or tiny? So to allow for those true comparisons, the frequency must be expressed as a rate. A rate measures the occurrence of a particular event, whether it's getting a disease or, sadly, death, in a defined population over a given time period. It's really a fundamental statement of the risk of developing that condition or experiencing that event. So when epidemiologists talk about a rate, they're not just, throwing a number out there. It's a carefully constructed fraction. You've got the count of events on top of the numerator. Then you have a clearly defined population group on the bottom of the denominator. That's absolutely crucial. And it's anchored to a specific time period. Usually it's a calendar year, but not always. And then, importantly, it's scaled. It's multiplied by something like 1,000 or 100,000. That multiplier, it's chosen simply to avoid dealing with tiny, tiny fractions and make the number easier to grasp. 10 cases per 100,000 people is easier to understand than 0.0001 cases per person. So those four pieces, numerator, denominator, time, and multiplier, that's what gives a rate its power. It reflects risk and lets you make comparisons. And we generally categorize rates. There are crude rates, which are just the observed, unstandardized rates. Then specific rates, which focus on particular causes, like death from heart disease, or specific groups like teenagers. And standardized rates, which are adjusted for factors like age or sex, which is really important for making fair comparisons between populations that might have different age structures, for example. Okay, so if rates give us that sense of risk and allow comparisons over time or between groups, what if we just want to compare two different quantities, two numbers where one isn't necessarily part of the other? That's where ratios become incredibly useful. A ratio expresses a relationship in size between two let's say random quantities, where the numerator is not a component of the denominator. It can relate to an interval of time, or it might be instantaneous, just a snapshot. And it's typically expressed as xy, like a ratio, or sometimes xy as a fraction.
Okay, so let me give some examples from our sources to make that clear for everyone. Think about the ratio of white blood cells to red cells in your blood. It's around 1 to 600, right? The white cells aren't part of the red cell count itself. They're separate things you're comparing. Or another example, the ratio of children with scabies compared to children with malnutrition in a certain area. Again, two distinct groups. Other common ratios you might hear about are the sex ratio, males to females, or even the doctor population ratio in a country.
Exactly. Now, a proportion is also a type of ratio, but here's the crucial difference. The numerator is always included in the denominator. A proportion indicates the relation of a part to the whole, and it's usually expressed as a percentage.
Right. So using an example again, let's say you count the number of children with scabies at a certain time in a village. You then divide that number by the total number of children in that same village at the same time. The children with scabies are definitely part of that total group. Then you multiply by 100 to get a percentage. That's a proportion.
And that's the fundamental distinction, the key takeaway for you listening. In a ratio, the numerator is not part of the denominator.
Yeah.
But in a proportion, it is always included. It's part of the whole.
Which brings us to what you called crucial earlier, and maybe the true unsung hero of all this epidemiological measurement. the denominator. That numerator, the count of events, really has very little meaning on its own, doesn't it? Unless it's related to a proper denominator.
Mm.
And choosing the appropriate denominator isn't just important. It sounds like a critical skill for an epidemiologist. It's what allows for those meaningful comparisons and gives us a true understanding of risk.
Absolutely. The denominator is, well, it's basically everything. It defines the population you're actually talking about. It provides the context. And denominators can broadly be related to the population itself, or sometimes they're related to the total number of events. So when we talk about population-related denominators, the mid-year population is a very common choice. It's usually estimated for July 1st. Why? Because population size changes constantly, daily even, due to births, deaths, and migration. So the mid-year figure is sort of an average representation for the year. But then there's the population at risk, which is such a crucial concept, really important. And it's one that can completely shift your understanding of a situation. It refers specifically to all those people to whom an event could have actually happened. Okay, think about this. A food poisoning outbreak in a town of 10,000 people. Let's say 50 people get sick. Now, if you calculate the rate against the entire town of 10,000 people, that's 50 divided by 10,000. It's a tiny 0.5% rate. Seems minor, right? But now imagine only 100 people actually ate the contaminated food at that specific picnic. Those are the only ones truly at risk. Suddenly, your calculation is 50 sick people divided by 100 people who ate the food. That's a 50% attack rate among those who are actually exposed.
Wow, yeah.
See, the population at risk totally flips your understanding. It goes from minor inconvenience maybe to major crisis for that specific group. That's the power of choosing the right denominator. It's restricted solely to those capable of acquiring the disease or condition. Another quick example. For calculating general fertility rates, the denominator isn't all people or even all women. It's restricted to women aged 15 to 49 years because, generally speaking, they are the population segment considered at risk of becoming pregnant.
That food poisoning example really drives it home. Okay, what other types of denominators are there?
Well, another important one, especially in research studies, is person time. This is often used in studies where you follow individuals over time, but maybe for different lengths of time, like in cohort studies. It's essentially a combination of the number of persons and the time each person was observed. So, for instance, if you have 10 people in a study, you follow each of them for 10 years. That's 10 times 10, which equals 100 person years of observation. It's a really elegant way to summarize the total experience of individuals who might have been observed for different lengths of time or had different exposure durations. There's also a variant called person distance, like passenger miles used in transportation safety studies. And, of course, denominators can be specific subgroups of the population. You might calculate a rate just for men, or just for people age 65 and over, or for a specific occupational group, depending on the question you're asking. And lastly, as I mentioned, sometimes the denominator isn't the population size at all, but it's related to total events. Think about the infant mortality rate. The denominator there isn't the total population.
It's the total number of live births in that year. Or the case fatality rate for a disease. The denominator is the total number of people diagnosed with that specific disease. And going back to your traffic accident example, calculating deaths per 1,000 registered vehicles, or maybe per million vehicle miles traveled, is often much more useful, much more informative about the actual risk of driving than using the total human population as a denominator, because many people in the total population might not even drive or use vehicles much at all. It gives a far more accurate picture of the risk associated with the activity itself.
What a journey. We've really peeled back the layers here today, haven't we? What started as seemingly simple things like measurements are actually, well, they're sophisticated tools. They go far beyond just counting. They represent this rigorous bedrock that allows epidemiologists to understand these complex health landscapes and entire populations and, ultimately guide effective public health action.
Precisely. And I think this deep dive into just the basic measurements really highlights the rigorous framework that underpins public health insights. It's not just guesswork. And knowledge like this is always most valuable when it's understood and applied. Critical thinking is just so essential, especially today, in a world where we're constantly bombarded with information, with numbers, with statistics. So maybe a final thought for you to consider. Now that you have a better handle on these foundational principles, rates, ratios, proportions, the mighty denominator, think about the everyday rates or ratios you encounter. You see them in the news, on social media, everywhere. Could applying these concepts, asking about the numerator, the denominator, the time frame, could that help you critically evaluate what those numbers are really telling you about a situation? Or maybe, more importantly, what crucial piece of the puzzle, perhaps what denominator, might be missing entirely from the story?